Welcome to Melac Online tutorial. Still on specific heat capacity and heat calculations. Now here is another question, and it reads that a tap supplies water at 30 degrees Celsius, while another supplies water at 86 degrees Celsius. Now, if a man wishes to bathe with water at 45 degrees Celsius, now calculate the ratio of the mass of hot water to that of cold water. Now, what are we looking for? The mass of hot water H to that of what? Cold water, MC. Alright, please, if you're new to my channel or probably my Facebook, please like. If you're on Facebook, like my page, share with your friends, and if you're on YouTube, please subscribe to my YouTube channel and ensure you get a notification of all my videos in physics and mathematics. Alright, come, let us get started. Now, in this kind of question here, now it tells you about two things. Now, a tap that supplies water at 30 degrees Celsius and another supplies water at 86 degrees Celsius. Now, this man wishes to bathe with water at 44 degrees Celsius. Now, the question is, how do we marry 86, 30 to 44? Now, here is it. Now, in questions like this, now there is a principle behind it. Now, since it involves hot and cold, now here is it. Now, take note that when hot water is mixed with cold water, now here is what happens. The hot water releases energy, okay? While the cold water receives the energy released from the hot water. Now, in natural sense, you can say that the heat lost by the hot water is gained by the cold water, if that makes sense. Now let's come back. Now generally we know that the general formula when it comes to specific heat capacity is this, that H equals to M, which is the product of the mass, the specific heat capacity of the substance, and change in what? Temperature. Okay, now let us assume that this is the quantity of heat released by hot water. Okay, so this is hot, okay. Now, and this is the heat also absorbed by the cold water, and CC, and okay. Now this is for the hot and this is for the cold. Okay, now it implies that as a particular amount of heat is released or lost by 86 degrees Celsius of the hot water, now a particular amount also is absorbed. The same quantity of heat that is lost from this hot water is also absorbed by the cold water, and at the end it boils down probably at equilibrium, yeah, because after the release of the energy, this one gains it, then they now settle at what? 44 degrees Celsius. Now, how then do we marry this? Now, it implies that the heat lost by hot water equals to what? The heat gained by the cold water. Alright, so it implies here that the heat loss by hot water is equals to the heat gain by the cold water. Now, if this is now true, and we know that the heat loss gives us this by hot water, and the heat loss the heat absorbed by cold water is this. So we can actually say that MH CH, then change in temperature for hot water equals to what? MC for cold water, CC for cold water, and change in theta for cold water. Okay, all right, now let us now marry this equation together. Take note, we are told to find the ratio of the mass. Okay, so which means mass and mass is what we're actually looking for, the ratio. And take note that since we are dealing with water, it has the same what specific heat capacity of 4200. In that case, we can actually eliminate it off since they are the same. Okay, so that we won't just bother ourselves. So we were left with what? MH, then change in theta for hot, then equals MC, now change in theta for cold. Alright, now to this end now, for this change in theta for hot, let's come here, then the parentheses. Now for our change in theta, now take note that since this is greater than the final temperature, okay, then we have that 86 minus 44, okay, because since 44 is the final end, okay, all right, and MC at this point we have what, 44, then minus what, 30. So here we have it. All right, okay, so what we now need to do, since it is the ratio of the hot water to the cold water, which means I just divide this by MC, okay, all right, and here we divide this by 86 minus 44, then here we have what, 86 minus 44. All right, so this will eliminate this will eliminate this, okay, and 44 minus 30, now this should give us you see, 44 minus 30 give us 14, then all over this should give us 42. So here we have that MH all over MC now equals 14 all over what, 42. Now 14 here 1, now 14 here should give us what, 3. So we have that the ratio of the hot water, that means the mass of the hot water to the mass of the cold water will be what, 1:3. Final answer. Alright, welcome again to Latent online tutorial. Now before us is another question in specific heat capacity, and this question reads that the temperature of a piece of metal of mass 9 grams is raised from 10 degrees Celsius to 110 degrees Celsius when it absorbs 108 joules of heat energy. Now determine the specific heat energy of the metal in joule per kilogram per Kelvin. Alright, if you are new to my channel and if you are new to my page, please kindly subscribe to my YouTube channel, like my page, and sure you share to your friends, families, so that they will learn this. Alright, now let us start. As I've always said, whenever you encounter questions like this in physics, the first thing first you need to do is to write out the parameters. Now, writing out the parameters will give you an edge on what formula to use. Now, we are given that the mass, let me write it here, that the mass of the piece of metal is 9 grams. Now, since we are having 9 grams here, take note that we are told to calculate the heat, specific heat energy of the metal in joules per kilogram. Definitely we just need to what, convert this to what, to kilogram. Now how do we convert this to kilogram? First of all, let us recall that 1000 grams now gives you 1 kilogram. Now in essence, always just remember that kilo here means 1000. Okay, this kilogram here, this kilo implies what, 1000. So if you have 1 kilogram converting it to what? Gram. What you just need to do is just this 1 times then the kilo, which is what? 1000. Then you have your gram. Now if it is probably 3 gram, I mean 3 kilogram, now it implies here that 3 times, then this kilo here is 1000. Then you end up having what? 3 kilogram. How do we convert 9 gram to kilogram? Now if 1000 gram then equals 1 kilogram. So what we just need to do is to divide this 9 by 1000, since 1000 gram will give you what? 1 kilogram. So by dividing it, that will be 9 divided by what? 1000. What you just need to do is to take your decimal from here. Since it's a whole number, then your decimal is actually after the number. So you count 1, 2, and 3. Okay, so your decimal here. Then how many gaps do we have here? 1, 2. So that will be what? 0.009 kilogram. So this will give us 0.009 kilogram. Okay. Now the next thing here, we're not to the from. Now since from the word from, which means it's starting from here and ending here. Since it is starting from here, so we will say that this is the initial temperature. That'll be theta 1. That'll be 10 degrees Celsius. And theta 2, that'll be what? 110 degrees Celsius. Okay, so, and it absorbs the heat. Our heat here is what? 108 joules. All right. Now, since we've written out the parameters, now this has now helped us to recall that in terms of our specific heat capacity, we have that H equals what? M, which is the mass of the substance, C, the specific heat capacity of the substance, and the change in temperature, where our change in temperature signifies what? Theta 2 minus theta 1. Alright, we're writing the equation where we have H equals what? MC, then in parentheses theta 2 minus what? Theta 1. Alright, let us plug in these parameters into the equation. Here we have that H, which is 108, equals the mass, which is what? 0.009, then times the specific heat capacity. Okay, that's what we're looking for. So here you have the C, then times parentheses theta 2 110 minus what? 10. Okay, so here we have 108 equals 0.009 times C times 110 minus 10 give us what? 100. Okay, and a quick one. Now what we don't need to do here, now since this is what we're looking for, we can actually multiply 0.009 times 100, and since we are dealing with just zeros, cancel this, that is 2, take your decimal 1 and 2, so we are left with what? 108 equals 0.9 C. Right, now the variable side by the coefficient of C, which is what? 0.9. We eliminate this, and our C then becomes 108 all divided by 0.9, and so this will give us 120 joules per kilogram per Kelvin. Final answer. I hope it is clear and well understood. Alright, thank you and God bless you. That calculate this final temperature of 2 kilograms of alcohol at 25 degrees Celsius when 20160 joules of heat energy is added to it, and we are given that the specific heat capacity of alcohol is 2520 joule per kilogram per Kelvin. Alright, if you are new to my channel, please kindly subscribe to my YouTube channel and ensure you click on the notification button to be notified of all my videos. And if you're on Facebook, please like, share, and drop a comment as regarding to this topic. Alright, now first, let's start. Now, first of all, when you encounter questions like this, it's very important that you write out the parameters in the question. Now, first of all, we are given that the mass of the alcohol, let's just signify it as MA as 2 kilogram. Okay. Now for the fact that this it means this is the initial temperature. So we can denote that let us say maybe T1, or you can just say theta1, depending. You have 25 degrees centigrade. Now when 2O, that probably 20,160 joules of heat energy, so we write that out. The heat equals 20160 joules. Okay, and we are given that the specific heat capacity equals 2520 joules per kilogram per Kelvin. Now, the next thing we need to look at now is to recall the formula for specific heat capacity, and which is given as H equals what? The mass of the substance. Now the specific heat of the substance and change in temperature. Now this change in temperature is denoted, that is change in theta, which is theta2 minus theta1, which can also be written as probably T2 minus T1. That is in the case if this is written as change in what? T, which is what? The temperature. Alright, now the next thing we look at now is, and we are told to find the final temperature, which means either T2 or theta2 is what we're looking for. Now writing this formula with regards to this, we have that H equals MC, then in brackets, parenthesis rather, T2 minus what? T1. Okay, now let us now fix in all these parameters into the equation. Then we tend to solve for what? Theta2, which is what? The final temperature. Now we are given that the heat, you write that out, 20160 equals, now the mass of the alcohol is 2, then times the specific heat capacity, which is given as 2520, okay, then times, then open parenthesis, the final temperature which we are actually looking for, Theta2 minus theta1, that will be 25. Now close. Now what we need to look at now is how to resolve this or simplify this, okay? And by calculation, 2 times 2520 will give us 5040. So here we have 21606 equals 5040. Then open bracket, theta2 minus 25. Alright, so since 5040 is the coefficient of this term, what we need to do now is to divide both sides by the coefficient of the term we are actually looking for. We have 5040, 5040. That's 20160 divided by 5040. So here we have 4. This will eliminate this, then equals theta2 minus 25. Now since here we have negative 25 here, what we just need to do is add 25 to both sides. Add 25 here, add 25 here. Now this will give us 29, then equals, the whole of this will give us what? 0. We are left with what? Theta2. So our final temperature, which is theta 2, is now what? 29 degrees centigrade. All right. Thank you and God bless. Bye. Okay, and here the question reads, now what amount of current would pass through a 10 ohms coil if it takes 21 seconds for the coil to just melt a lump of ice of mass 10 gram at 0 degrees Celsius if there are no heat losses? Alright, now let me give you a pictorial diagram of what this question is talking about. Now let us assume that this is the lump of ice. Let us say this is the ice. Okay. Now this coil, let's assume here, okay, now this is connected to a source. Okay. All right. Now, this ice at 0 degrees. Now, with the heat from this coil, the ice absorbs this heat from this coil and melts to become water. So let us assume it's melted and probably become water. Okay? Although flows down, okay, as usual. Now, but where am I driving at now is that ice. Let me just put this is this way. So originally from this ice to water, now still at 0 degree Celsius. Okay, now the ice at 0 degrees Celsius melt to becoming what? Water at 0 degree Celsius. Now this temperature constant is what we call the latent heat. Now a case whereby a substance changes state without a change in temperature. So this ice in its solid state changing to liquid, okay, at the same temperature, or probably without a change in temperature, is what we call what? The latent heat. And that is what this question is actually referring or talking about. Alright, so but how then do we solve this? Now let us recall that latent heat is given as the heat, the specific latent heat is given as what? H equals what? The mass of the substance and the specific latent what? Heat. Okay, so this is the heat generated or absorbed when a particular change is occurred from the solid to what? Liquid at a constant what? Temperature. So now let us now marry that with this. Now the heat given or supplied by this coil equals to the same heat absorbed by the ice, okay, making it to change from the solid state of ice to the liquid state, okay, from still at 0 degree Celsius. So we can say that the heat supplied by the coil equals to the heat gained by what? The ice, okay, changing it from ice to water. So now, and the electrical heat here will be given as what? I VT, then equals to ML, where L here is the latent heat of what? Fusion of what? Ice. Okay. So writing out the parameters, we are given that the resistance of the coil is what? 10 ohms. Time is 21 seconds. What else are we given? The mass of water, sorry, the mass of ice equals 10 gram, and the temperature equals what? 0 degree temperature. What else are we needing here? And we are told that what amount of current. Okay, so we are looking for the current and the specific latent the latent heat of fusion rather is given as of ice is given as 336, okay, joules per gram. Okay, any other thing we need to put in place? No. So, but in this case here that we have IVT, okay, but we need to look at, okay, I is here. Now V is not here, rather it's R, but T is here. So let us recall that V equals what? IR according to Ohm's law. Okay, now making V the sort of formula here. Okay, making V. Okay, since V is equal to IR, so let us plug in V for, let's plug in IR for V here. So you get to have I into what? IR, then T equals what? ML. So here we have I squared RT equals what? ML. So we can now plug in. And what exactly are we even looking for? The current. Okay, so divided multiplied by IRT, so our I squared equals what? ML all over what? RT. Okay, let us just solve this one first. Then the mass of the water is 10 gram. Now, since this is given in joule per gram, so we can just leave this as gram. Then times 336, which is the latent heat of fusion of ice. Then all over the resistance, which is 10, times the time, 21 seconds. Okay, so here we have, okay, let's just say the square root. Now we actually ignore the negatives. We are meant to have plus or minus here, but we just ignore the negative. So here we have that 3360 all over 210. And this will give us 3360 divided by 210. So here we have 16. So the square root of 16 is now what? 4.0 amperes. Okay, so here is the amount of current that we needed to pass through this coil to melt the lump of ice of mass 10 gram at 0 degree Celsius. Still on specific heat capacity, and it reads that an immersion heater rated 2.0 amperes 240 volts is used to boil water from temperature 53 degrees Celsius to 100 degrees Celsius. Now if the mass of water is 2.5 kilogram, determine the time taken to boil the water. Alright, so let me just give you a pictorial diagram. Now let us assume that this is the bucket of water probably in a basin. Okay, now this immersion heater, let's see, this is the kind of heater that actually made use of Okay. So this is the source of heat, the source of current rather. Okay. Now, from the question, the initial temperature of this water before the immersion of this heater is 52 degree. Okay. Now, as this heater is immersed and powered, okay, by 240 volts and the current of 2.0 amperes. Now it now increases from 52 to 100, which definitely makes it what? To boil. Okay, now it implies that the heat given, all right, by the electric heater is absorbed by the water, making it what? To boil or to increase, rather, okay, to boil and to increase from 52 degrees to 100 degrees. So the heat supplied by the electric heater, that is electric heater, electric, okay, let me just put H, yeah, heater, then the heat supplied by the electric heater now equals to the amount of heat absorbed by the water. Okay, now looking at this, so we can conclude that the heat supplied by the heater equals to the heat absorbed by the water. And take note that this is electric what? Energy. Now to that effect, now for electric energy, heat is given as IVT, all right, where I is the current, V is the voltage, and time, T is what? Is the time. Okay, all right. So let us now equate, and the heat absorbed here is our normal MC, then changing what? Theta. Okay, all right. So we can see here that H for the heater, that is the electric energy supplied by the heater, equals to the energy absorbed by the water. So here we can say IVT equals MWCW, then change in temperature. Okay. Okay. Now we're giving current. So our current is 2.0 amperes. Our volt is or voltage is what? 240 volts. Then our time is what we are actually looking for. And is there anything other? Okay, the mass of water given is 2.5, and temperature change, that's the initial temperature, let's say 1, from temperature 52 now to T2, which is what? 100, at which the water boils. Okay, is there any other parameter we are missing? Okay, that's the specific heat capacity. Okay, any other thing again? No. All right, now let us now plug it in here. Our current here is 2, so that is 2 times our volt, 240, and our time is actually what we're looking for. All right, then the mass of water is 2.5 times the specific heat capacity of water. We're given 4.2 times 10 raised to the power 3, then times temperature change. That will give us 100 minus 52. Okay, so we'll multiply this will also give us 480T, then equals, solving this is 100 minus 52, to give us 48, right? Okay, now let us multiply all this together. Now this one in normal form, here you have what? 4200. Okay, so here we have 2.5 times 4200 times 48. So this gives us 504000. Now divide both sides by the coefficient of t, which is what? 480. And here you have divided by 480. So we get to have 1050 seconds. So the time is 1050 seconds. Final answer. Alright, if you love what I've just done, please subscribe to my YouTube channel and ensure you click on the notification button to be notified of all my videos. And also, please do not fail to share this on Facebook. Thank you and God bless you. And it said a piece of copper ball of mass 20 gram at 200 degrees Celsius is placed in a copper calorimeter of mass 60 gram containing 50 gram of water at 30 degrees Celsius. Ignoring heat losses, calculate the final steady temperature of the mixture. And here we have the specific heat capacity of water to be this, and the specific heat capacity of copper to be this. Now to bring this question to a source of reality, let me draw this. Now that here is the calorimeter, okay, now, and we are told that the copper calorimeter of mass, so this one has a mass of 60 gram, now containing 50 gram of water. So let's assume this is the water here. Now the water itself is 50 gram, okay, and the temperature here is 30. All right, so which implies that both the calorimeter and the water has a temperature of 30 degrees Celsius. Now a piece of copper ball of mass, okay, now look at this. This is the copper ball, okay, let's say this is mass 20 gram. Now, and the temperature is 200 degrees Celsius, okay, and you can see that even this one is very hot, okay, and this one just within room temperature, okay. Now look at this. If this metal at 200 degrees Celsius enters this calorimeter, what do you think will happen? Okay, all right, now here is what happens. As it is being dropped into this water, okay, this is the ball. Now what happens here is there is a loss of heat, okay, by the ball, and as it enters, most likely this will what, increase. So there will be an increase in temperature here, okay, and there will be a reduction of temperature here. Now this reduction of temperature here, whatever temperature is being given out or energy that is being lost by the ball, is the same energy that we what gain by the water and calorimeter, okay. So which implies that the heat loss by this ball will be equals to the heat gain by the water in the calorimeter and the calorimeter itself, okay. Now if we tend to understand this, now this question is then solved, right? Now look at it. Take note that the heat loss by the copper calorimeter, okay, now equals to the heat gained by water plus the heat gained by the calorimeter. Okay, now here is the formula or the equation we'll be making use of. Okay, and let us also recall that the heat is in itself equals to H, which is a product of mass, specific heat capacity, and the change in temperature. All right. Okay. Now, since we've understood this now let us now come back to solving this. Okay. Now let us know that the parameter, that the mass of the copper equals 20. Okay. Now, since the unit is given in joules per gram, so there's no need of converting this to gram. Okay. Now the temperature of copper, that is the initial temperature of copper, is 200 degrees Celsius, and the mass of copper calorimeter is given as 60 gram. Now the mass of water is given as 50 gram. Okay, now the temperature of the calorimeter also is what, 30, and that of water is what, 30. All right, now the final temperature to which we are looking at now is theta. Okay, because the same temperature or the amount of heat that the copper ball will lose is the same amount of heat that the water and the calorimeter will gain. Alright, so let us now use this parameter, fit it into this. Then here we have for copper first, which is MCU CCU, okay, then 200 minus, which is this, okay. All right, then equals for the water. So here we have for the water, that is the mass of water, the specific heat capacity of water, then the final temperature, then minus 30. Okay, now plus for copper calorimeter, mass of copper calorimeter, specific heat capacity of calorimeter, and the final temperature minus the initial temperature. Okay, now let us start solving. Now this is what we'll be working with now. Okay, all right, so for the mass of copper, which is 20, that'll be 20 times the specific capacity of copper is 0.4, then 200 minus the final temperature, then equals to, now the mass of water, this is 50, right? Okay, that will be 50, now times 4.2 as it is given, then theta minus 30, now plus copper, that the copper calorimeter, the mass is 60, then times that will be 0.4, which is the copper calorimeter. Now since the calorimeter is made up of copper, so definitely it will have the same specific heat capacity as the copper ball. So here you have theta minus 130. Okay, now you can now resolve. Okay, now 20 times 0.4, so give us 8. 200 minus the final temperature equals now 50 times 4.2, then we have 210 into final temperature minus 30, then plus 60 times 0.4, that will be 24 into what, theta minus what, 30. All right, now looking at this, for us not to stress ourselves more, you can see that 210 has this term, theta minus 30. 24 also have this term, theta minus 30. So that 210 and 24 has a common term of what? Theta minus 30. So let us factor out theta minus 30. So here you have, okay, opening this bracket here. So that will be 8 times 200, that will be 1006. Then times 8 times theta, that will be 8 theta. Then equals, now factoring out, you have what? 110 plus 24 into what? Theta minus what? 30. Okay, so solving this one will give us the right hand side, 210 plus 24 will give us 234 into what? 30 minus what? Okay, so let us now open the bracket for this. We have 1600 minus 8 theta, then equals to 234 theta, then minus 234 times 30 will give us 7020. Okay, let us now collect like them. Theta for theta, whole number to whole number. So let's bring 7020 the left hand side. We have plus because it has minus here. 7024 then equals 234 theta minus plus, yeah, because 8 theta is having minus here. As moves here, it becomes plus. Okay, let us now add down plus 1600. That's for the left hand side. We have what? 8620 then equals 234 plus 8. You have 242 now theta. If you are dividing both sides by the coefficient of theta, which is 242, then our theta will be 35.6, okay, approximately 0.6 degree centigrade. All right, so this is the final steady temperature of the mixture. I hope it is now clear. Please share to your friends. Thank you and God bless you.